Okay, welcome again, everyone. This is the first in a series of sessions that we will be discussing a very simple perspective using the idea of the physics of electronics to uh, create the rules that we use to design our printed circuit boards. This class, I call it Electromagnetic Fields for Normal Folks, because the whole idea is that we want to focus on what things really make a difference, and those are quite simple, and that's what the class is focused on. There's a lot of high level physics behind all this, and if there are any physicists in the audience, then I apologize, because this perspective is very basic, but it's very effective. And we will get pretty deep into what my understanding has been. And I'll try to use very simple language because I'm just a simple man as well. I do not have a physics degree. Actually, don't even have an electrical engineering degree. I grew up in the industry uh, from the very beginning in 1980 and have been able to work with some extraordinarily patient and experienced mentors. And my whole path has been blessed by these individuals and the time they've allowed themselves to participate with teaching me the way of the world. My computer is not behaving. So again, I work for NXP. NXP was the silicon arm of Philips, and I worked for Motorola. And then about the same time that NXP was spun off from Philips, Motorola spun their semiconductor arm off as Freescale Semiconductor. And so I worked for Freescale for a number of years still. So it was Motorola Freescale. And then at some point a few years ago, NXP, in an effort to get more involved in automotive, which was Freescale's sweet spot, they merged with Freescale and we became NXP. So a very nice, very global company, very focused on the people in the company, focused on to managing the resources of the planet, and one of the most responsible companies that I know of. I really have been blessed to be working with that series of companies, and the opportunities it's given me and my colleagues have been just wonderful. So that's a little bit about NXP, and they let me do this. So I'm very excited to be part of this whole effort to create training materials and disseminate this information. My disclaimer is the same in every class. I teach the same things over and over and over again. This is partly driven by the fact that when I was trying to learn this, it was very difficult to accept these simple principles because I'd been brainwashed into believing that electronics was complicated and that I had to uh, do some very difficult things in order to be able to do my designs. So I had to hear this stuff many, many, many times. In fact, it took more than 10 years before I was finally able to put my faith in the physics and the impact of three-dimensional structures in the behavior of the fields, and finally come to believe that it was all about the space. So that works better. So like Professor Robank said, this is my 43rd year in electronics for the Motorola Freescale NXP. I've been in automotive since 1987. I moved from where I was working in the Phoenix part of Motorola in the microcontroller development systems group. So I was a toolsmith where we worked on some of the most advanced systems, starting out with the 8-bit machines, the 6800 family, but in the end, I was working on 68,000, 68020 in-circuit emulators. So I thought I was like hot. I was doing the highest performance processors and doing tools, which everybody was afraid of. And I thought I knew everything there was to believe to do with electronics. And I came to some very quick realizations as the industry was changing that what I was doing was not the right methodology. And to me, EMC was a magical mystery world. And until I met Ralph Morrison, it was something that I just couldn't get my head around. And it seemed to be pretty much the whole world. We would have problems with customers and EMC with their systems, and we would try to fix things, and you'd put band-aids on. You'd cut this trace or add a capacitor here or put a ferrite and inductor in. We would hire outside consultants, and they would come in and spend a month looking at the behaviors and then give a list of components they thought should be added to the design in order to become compliant. And it was hit and miss. It wasn't engineering. It was just as much voodoo to those experts as it was to me. So at a certain point, I found that if I didn't go find the knowledge and become a specialist, then my customers wouldn't be able to create products that they could sell. And from a very selfish perspective, if they can't sell their products, they're not going to buy anything from me. And my job is to sell silicon. I'm a sand salesman. And if I can't enable my customers to be successful, which is the foundation of being an applications engineer, then I really needed to find some way to help them be successful. And that's what my mission became. So next, I want to talk a little bit about Ralph Morrison. If you don't know who Ralph is, please take some time later today and Google him or go to the ralphmorrison.com website. Ralph was one of the founding pioneers in our industry who really tried to tell everyone from the very beginning of his career that energy moved in space and it wasn't electrons flowing through wires. And Mr. Morrison was the one who wrote the first textbook, Grounding and Shielding, in 1967. That was the foundation text for all of the industry. In fact, if you ask some of the acknowledged giants, Henry Ott, Howard Johnson, Lee Ritchie, where they got their start, they would all say, and I've had people actually ask them these questions, that it was with Ralph's book, Grounding and Shielding, that he wrote in 1967. So I'm going to get a laser pointer or a pen, that's even better, that I can use to try to show you. This book is the foundation for our industry right here. Yeah, that doesn't work. Sorry. So Ralph's book was the first one in 1967. And he went forward in his career writing a total of 13 different books. The last one was Fast Circuit Boards, Energy Management, that Wiley, who's the big publishing company for textbooks and engineering, asked him to write at the age of 92. So Ralph was active up until the very end. He was, in fact, studying quantum mechanics because he was convinced that there was more to electronics than what people understood and was determined to find the key. And so he was very active even then. He was still playing the violin. He was still driving. And it was just really a very sad moment in my life when Ralph passed away in 2019. He got his first degree in physics in 1949. He had been a radio technician in the Army during World War II. And he said that was the best job because there were so few radio technicians that they were kept as far away from the danger zones as possible. And he took that learning, and after he got out of the military, he had been a violinist his whole life. So he was asked to join the traveling symphony orchestra that the Army had to go through Europe. And he said this was a wonderful time for him because he got to play some of his favorite music, classical guitars, and to visit these cities where his favorite composers lived in and play their music. So it was a very exciting time for him. And then when he came back, he used the GI Bill to get his bachelor's in physics. He actually was studied some under the famous Feynman, and then finally got his double E in '64, a master's. So here's Ralph when he was young and still in the Army. And the picture to the right is Ralph at his 90th birthday. He did a recital where he was playing violin, and then this is the orchestra that he was playing in. His wife Elizabeth was a cellist. They had a string quartet, and one of the joys was when I would visit Ralph, they would invite their friends to come over, and I would get to have dinner with Ralph and Elizabeth, and they would have their friends play this fantastic music in their home, and it was pretty great because that would be the end of a day where Ralph and I would talk about electromagnetic fields and argue about physics and have just a great day where he was trying to patiently teach me the reality of the world of electronics and help me unlearn everything that I had been focused on my whole career. And then the last book he wrote was Fast Circuit Boards. And I would suggest to you, if you're going to buy one book to have as a reference, this would be the one. Ralph writes in a very useful fashion. He has chapters where he identifies concepts. He lists the science behind it, the equations, the drawings, and then he has a recap at the end of each chapter. So they're very easy to understand. But what I want to share with you is something that I missed for years. At the end of every one of Ralph's presentations, he always would say this: buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. And this was so profound. It really explained all of the mysteries of electronics. If you understand this, that the energy's in a space, and instead of designing wiring, that you design the spaces using the conductors as the boundaries, then you will find that you're going to be successful. We were not taught this correctly in school, and the industry has suffered profoundly from this misconception of behaviors. In fact, I want to suggest that more than $1 billion is wasted every year by very well-meaning design teams that put together circuit boards and send them to be tested, knowing they're most likely going to fail. And then they have to redesign the board, try to get them assembled in a hurry after they rush the fabrication of the PCB, and then send it off again with very little hope that it's going to pass the second time. In fact, most of my customers will admit it's 3 to 5 different respins for the circuit board before they achieve compliance. Nobody budgets for the time, nobody budgets for the expense, and the result is that product development is stopped during the time when you're trying to get this current product out the door. And it's because we weren't taught right. And the design rules put the focus on the wrong ideas. And today we're going to talk about a very simple perspective of the correct way that the electromagnetic fields behave. So part of my mission was to help people to learn faster than me. I don't want it to take 10 years for you to finally believe in geometry and three-dimensional structures. So I wrote this song that I played over and over again before the class to Megan Trainor's All About That Bass. And I wrote this, It's All About the Space song. So this is available for your pleasure on YouTube, and hopefully you'll take these words to heart. It really gives you the real basics of the electromagnetic physics classes in a very few words that are easy to understand. So why suddenly does everything not work? And when I was started in electronics, I was a radar technician for the U.S. Air Force. So I learned how to use a voltmeter and an oscilloscope, and I was NASA certified solderer, and went to work for Motorola in 1980, and everything we did seemed to work. I moved into engineering. I wire wrapped a 68020 single board computer, and it worked just fine. And there were no special considerations for, placement of capacitors or transmission lines or any of those scary things. And all of our design rules seemed to be based on the fact that whatever we did seemed to work. And then suddenly things stopped working. And what happened? Well, the big thing that happened is we started shrinking the transistor sizes. There was the pressure from customer marketing and purchasing to reduce costs. And the way you reduce costs in semiconductors is you try to get more die per wafer. So you start shrinking things. And as we started doing that, the switching speeds of these devices, excuse me, it's ratiometric. So the only algebra you need to know is algebra. If something gets smaller, it switches faster, and it's the same percentage. So no matter what now, even, the smallest micro that you can buy is probably in 55 nanometers. So it's switching in many, many gigahertz. And things are now pretty much all RF. And these changes, this reduction in geometry, is what's really driving the failures of our systems. So the changeover point seems to be Ralph was all about nanos. And when I first started working in the industry, everything was described as a percent of shrink from the integer design rules. And so, 85%, 65%. And these were reductions in geometry used in the photolithography process. But once it got to where they were talking about nanometers, things are in 120 nanometers, 180 nanometers, 90 nanometers, or you're looking at things that switch in nanoseconds. At that point, the traditional let's just hook it all up and make it work fell all apart. There was no longer any good management of the fields. And it was because the physical size of the structures that we're putting these chips into was large enough now, related to the speed at which they switched, that they started to become involved in the delivery of the energy. The same time we're shrinking the parts, the requirements for compliance have been increased. So they've been extended into lower and higher frequencies. The amount of energy you're allowed to radiate has been reduced. The amount of energy you have to be resistant to has been increased. And we're giving you parts that are better at making noise at higher frequencies and are much more susceptible to interference. So everything's going in opposite directions, and we still haven't really done anything to change how we design these systems. This is a completely new ballgame. What I have found, and I'm soliciting inputs for this list, there are only 3 universities that do a really good job of connecting the electromagnetic fields courses, the science of electromagnetics, to the engineering classes. The first one was what was formerly the University of Missouri-Rolla, and they've been rebranded as the Missouri University of Science and Technology. They teach a connection between fields and electronics. They do research where they build structures and test their behaviors. They document all this. And if you ever work with any EMC consultants, the very best ones are most likely graduates from this school. Clemson has a program because one of the principal researchers at Missouri was Dr. Todd Hubing, and he moved to Clemson as the endowed chair of the Michelin Automotive Technology Center. So Dr. Hubing took his field-centric perspective to Clemson. And then most recently, this is the one I've added in the last couple of years, I identified that Grand Valley State in Western Michigan is working with an external EMC consulting company where most of them are graduates from the Missouri one. So they now have started making the connection between electromagnetic fields and electronics. And they're giving the engineers from these schools the right skill set to design systems properly. What I had to do was start going to conferences. My first conference was PCB West. 5 minutes into my first class, which was with Mr. Rick Hartley, I knew that every design I'd ever done worked by accident, not by my skills. And all I remember thinking was that I sure hope my boss doesn't figure this out, because I'm supposed to be, know what I'm doing. I'm a senior engineer. I really need to know electronics. But from what I learned at Rick's 2-day signal integrity class was that I really was wrong on the whole thing. There are other places to get training. IEEE EMC Society hosts events around the world. They try to get the experts in fields to try to teach these. I work with some other signal integrity engineers, and we do a week once a year during normal times where we teach classes. I've been teaching at DesignCon Embedded Systems Drive World for a number of years. I try to host classes as often as I can, either at industry conferences, at NXP conferences, or special classes for my customers. And now, to add to this list, PCBAfrica is a place where you can get signal integrity and EMC training, because Professor Obank has made it his mission to share this information. There were just so many myths that I was taught and believed them blindly. It really was, I feel a little bit sad that some of these things I believed without having any deeper thought than in fact, my mentor told me to do this. And this is where it takes the unlearning. So actually, the less experience you have, the more likely you are to accept these concepts I'm going to discuss with less resistance in your brain. I resisted it very strongly. It took more than 10 years for Mr. Morrison to finally beat the circuit theory out of my brain and get the field theory back into there where it belonged. We talk about the foundation of electronics. My perspective was always that fields were something somebody else had to worry about. They're invisible, they behaved, they follow the trace. That's probably the only thing that I had right. They avoided open spaces. They're somebody else's problem. They're only important in RF and power supplies, and only for farmers. They were nothing I wanted to deal with. I was a digital circuit designer. I could do Boolean algebra, and I could draw schematics, and I could hook pins up, and it seemed to work until we got to the nano world, and then things fell apart. So one of the things I got from Mr. Morrison, and I have a lot of his slides in this class, because what he was trying to teach was so important that we needed to pay attention. So he talks about volts and amperes versus electric and magnetic fields. We like volts and amperes because it's simple algebra, again, which is really all you're going to need for what I'm teaching today. we thought about voltage. It's something you can measure easily with a voltmeter. You hook your leads to the circuit and it shows 5 volts basically instantly. And then amperes are something running through a wire when you hook an amp meter up. Those are easy to use concepts, and we have instrumentation that's low cost that you can use to get an idea about this. But our perspective of what voltage is and what amperes are is wrong. And that's where I want to try to get things around. It's really related to the electric and magnetic fields that are being used on the circuit board. And the missing point is here. When I try to measure voltage, it's going to be, it shows instantly on the meter. And so for our perspective as humans, it happens at once. So that suggests or confirms the perspective that current flows in a loop and it flows instantly whenever you hook up a circuit. But that's not true. When you hook your voltmeter to the circuit board, it takes a finite amount of time for the field density in the space between the leads to match the field density on the circuit board. It takes milliseconds before there's actually voltage, which is field density per cubic volume in that space. So it's not instant, and that's the first missing link in circuit theory. So, to take it a little farther, one of the great tools that we have is an oscilloscope. An oscilloscope lets you look at changes in voltage over time. So you take your oscilloscope probe and your ground lead and you hook it to your circuit board, and you can see changes in the voltage over time. And it looks pretty interesting. But again, it takes a finite amount of time to fill the space between the ground lead and the probe, faster than your 2 big long leads on your voltmeter, but it still takes time. And in my naivety, I found that if I needed to look at something that was switching very fast, I needed a FET probe. And I was like, FET probe, FETs are faster, right? That's not why they were allowing you to see faster circuit signals. It's because on a FET probe, you have a really tiny ground lead, and it has to be very close to the signal point. So it takes a whole lot less time and less field to fill that space than it does with the 3-inch long ground field. So you can see changes in field density faster because it takes less time for it to happen. Interesting. It's time and space. So fields are everything. It's easy to measure volts and amperes. It's difficult to measure the fields. The volts and amperes are sort of a artifact of fields, and we'll talk about what amperes really are in a minute. And in our systems today, some of it's the clock rates, and everybody seems to think that's the most important thing. But it's the rise time, how fast the switches turn on, that make all the difference in how the fields behave as they move through the space. So now we worry about the space and how fast the switches turn on and off. So I always put Maxwell's equations in here because you think about the world that Maxwell and his peers lived in. They were figuring out these incredibly important concepts, basis of our science, with basically stone knives and bear skins. And these concepts have become the foundation of our industry. Unfortunately, because these are scary equations, most people don't understand them. Ralph could spend all day explaining them. I'm not a physicist, and I don't do calculus anymore because I forgot all that. So the idea is that these guys were all extremely intelligent, and their intuition was unbelievable. So Maxwell was smart, but you don't have to know calculus or understand the deep parts of physics to be a successful PC board designer and electrical engineer. Here's the missing piece. Maxwell's equations are about the interaction between electric and magnetic fields. They aren't talking about electrons or holes moving. And here's the thing that I feel pretty stupid because I missed this for most of my career. The electromagnetic fields on a circuit board, it's the same energy as radio. All of us believe in radio, and it makes our world. If it was electrons moving through wires, there wouldn't be any radio. Think about that. We somehow decided that when you take the energy and put it on a circuit board, it changes from electromagnetic field moving in space into electrons flowing in the conductors. And that's why we have so many problems now. It's all about the space. In fact, to take this further, there aren't any wires connecting us to the sun. Light energy is just electromagnetic field energy at a much, much shorter wavelength. We wouldn't be here. All of our world told us that it was fields in space, not electrons in wires, and we as an industry completely ignored that fact. This is what you have to let go of in order to be successful in today's world. Talk about current. Current is not electrons flowing through wire. Current is something flowing, a physical thing, a substance, a gas, an electromagnetic field that are moving through a space. Water moving through a river is gallons per minute. The banks of the river have nothing to do with the movement with the water. They just show the water where to go. The same thing is in electromagnetic field. An ampere is a coulomb per second. A coulomb is a finite amount of energy moving through a space past a certain point in it. It's something we can understand as a flow, and it takes time to go from where it is to where it's going. Time is important too. That's a missing part of circuit theory. It's how many coulombs of field are moving past a space that's in a transmission line where you're trying to deliver the energy. This is the slide that you want to put on your wall. This is what took me a really long time to finally believe, and then to be able to draw it into something that's very simple. This is all about triplets. It takes 3 fingers to count all these things. To contain electromagnetic field energy, you just need 2 conductors separated by a space. You only get 3 components in your entire systems. You get a conductor, you get a space, and you get a switch. The most powerful microprocessor is just billions of switches. And all the switches do is add or remove spaces for the energy to move through. And then there are only 3 things you can do with field. You can store it in here, you can move it as the switch closes, or you can convert it to kinetic energy. You can move something, drive a motor, wiggle a speaker, heat up a filament in a light bulb. That's all there is. This isn't rocket science. This is really simple, and they made it so confusing that everybody makes bad decisions in their designs. If you can take this and convince yourself that this is the reality, then you're going to find that your systems will work properly. And to talk a little bit in the defense of the circuit people, and this is kind of a new revelation to me, is when you look at a charge that's stored between 2 conductors, there has been charge movement. So you've got one of the conductors has been depleted of some of its electrons, and the other conductor has had its electron population increased. And that's where you get the charge in that space. When you just got a space with nothing connected, all the charge is stable. So everything that's been displaced from one conductor to the other has happened, and it's just sitting there. The electric field as a result of some displacement of electrons. As you start to close a switch, in the case of a mechanical switch, nothing happens until it gets to the point where it's touching. But in a semiconductor, it goes from a very high resistance to a very, as it starts to change to a lower resistance. What happens is this field that's happy here on the left will start to see a conductor that has not been depleted. So as it sees more material where that electrons have not been depleted, it starts the displacement of those electrons from one conductor to the next. That is how it sees that it needs to move to this new space, is it sees spaces where the charge has not been displaced. And so that displacement current occurs at the wavefront as this energy starts to move into here. And the faster the switch turns on, the faster that the energy displacement has to occur. So you end up with a much smaller wavefront. The surface area is reduced. When a switch is slow, what happens is that the amount of displacement occurs on a much slower rate of time. So it only starts to happen. So you don't get as much activity on that wavefront when the switch is closing very slowly. And that's why we were lulled into submission by slow transistors, because the displacement current was spread out across time and the physical space in this conductor. And it wasn't energetic enough to cause problems. So this is the idea. And so from that perspective, yes, there is some current flowing in a loop, but it doesn't carry the energy. It's an artifact of the moving field. The field is really what's taking care of everything. So hopefully this makes some sense. But these are the triplets that make up your new world based on physics. Like I say, it's not rocket science. This is simple stuff. They lied to us. So look at this. Here's the field stored to the left. I have one conductor in green, and I call this the continuous conductor. We also think of this as ground. To quote Dr. Hubing, thou shalt not split ground. There is one ground. It is the same conductor from the source of the energy to the load. Next to that is the continuous dielectric, and that's the space where the energy moves through. So starting at the power supply, there's a dielectric that has to be continuous next to the continuous conductor. So two of the three components are already defined in where they need to be in your circuit board. Then you have a switch. As long as the switch is open, there's no movement of field because it doesn't see any materials that haven't had their electrons depleted. There's no displacement required. It sits here. There's no field here. This is the switched conductor, which is what we use to add or remove spaces. This isn't to make current flow in the loop. This is to make the field move into the new space. So as the switch starts to close, like I said, the field starts to see material where the electrons have not been depleted, and it makes them start moving in the displacement current through the dielectric, and the field then starts to move into the new space. It doesn't see the load. It just starts to move into the new space, and it takes time. Once the switch is closed, the fields will move until something happens. At this point, as far as this field is concerned, it's a short circuit because all of the energy that can possibly flow through this space, which is determined by the thickness or the width of the dielectric, the material that it's in, and the width of the conductors, will tell it how fast and how much energy it can move. But it has no idea what's at the other end. It just knows everything it's got is going to move here. So it moves into this new space until it finds the other end, and then something will happen based on that what the load looks like. But it hasn't seen the load, and it takes time. This is just like turning on water into a hose. There's no water coming out of the hose instantly. If you turn on the faucet, it takes a few seconds for the hose to have water coming out of the other end. That's how fields behave. It's exactly the same. It takes time, and the amount of energy is limited by the impedance of the transmission line, just like the diameter of the hose limits the amount of water that can flow through it. When I open the switch, this field here no longer sees any place where it needs to be depleting. So it stops moving. The field on the other side of the switch will keep moving, and it's whatever it does is determined by what's at the other end. If there's an open switch, then it will find equilibrium where the voltage will be stable. If there's another switch, this will then move into another space somewhere down the line. So into a microprocessor, it's a giant switch array, and it's turning on and off and moving field here and there, just like a big plumbing array. Nothing magic here. The behavior is something you can count on. And all we have to do is figure out where to properly place the switched conductor. So this is an IC, this is a transistor, this is a relay, this is a voltage regulator. All those are used to control the space that's connected to the source of the field, the power supply. So we develop products that generate, control, and consume electromagnetic field energy. That's not what we were taught, but this is the reality we live in. You know, circuit theory talks about electrons moving in a loop. That happens after the field moves. When you turn on a switch, you add a new space, and the moving field is how you carry the energy. You take the E field, you fill the space. Once the E field is established, then the H field transmits the power. And that's how things work. It's very simple. Ralph described it as like a drive shaft in a vehicle. He says once you establish the electric field and then you're consuming it at the load, that the magnetic field is what carries the energy. Again, this isn't what I was taught. This isn't what I was shown how to use. You know, I was just totally in shock. And how do I understand this? You know, I trusted all my professors and mentors, and everything seemed to work. And, you know, the problem was things weren't so bad, they always failed. And we mistook that for they were correct. Not so bad it makes it fail doesn't mean it's right. And we never looked into that. So there definitely was something we were missing in our methodology and our training. So it's all about the space. And you really have to focus on this. And I'm going to say space so many times, you're going to be sick of it. But if you aren't absolutely convinced that the energy is moving through space, then you're going to continue with the rest of the industry and design circuit boards that you're probably going to be expecting to fail. So again, current flow is a measure of the field in the space between the conductors. The things that happen, though, are we already understand that it starts by moving some electrons. So it's interacting with the outer molecules in the crystal lattice of the metal, the copper in most cases. It also, because the electric field is pushing on these outer valence electrons, it's causing these molecules in the conductor to start to vibrate. So some of that electromagnetic field energy is converted into kinetic energy. Remember, you can only do 3 things with field. One of them is to convert it to kinetic energy. So this bullying of the outer layer of molecules in the conductor is causing a reduction in the total amount of field energy because some of it's being converted into heat. That's what voltage drop is this resistance is where some of the field energy is converted into kinetic energy or heat. A resistor is a great example of a device that's designed to react to a certain amount of the field energy and convert it into heat. So when you use a resistor to drop voltage, it really does that. It consumes, if you got 5 volts here and you need 3 volts and it's going through a resistor, 2 volts, or which is coulombs per cubic centimeter, are being converted into kinetic energy. It doesn't disappear, it gets converted into heat. When you design your power supply wrong, so that you do not have the right transmission line to match the amount of field you are needing to move through that, you're going to have energy, excessive energy, converted into heat. And very simple to understand. The same thing also happens in the dielectric. There are molecules in the dielectric that the electromagnetic field interacts with and causes them to vibrate as well. So you lose some energy in the transmission line, both in the metal itself and in the dielectric, unless it's a vacuum. The other thing is we say that the fields move slower on a PC board than they do in vacuum. That in vacuum, it moves at the speed of light. Electromagnetic field always moves at the speed of light. The thing that we seem to miss is it doesn't go through matter. Electromagnetic field only goes in space. So in outer space, there are very few molecules, so it moves as fast as it can. And that's based on some quantum theory that nobody understands that yet. Once it gets into the atmosphere, there is a higher density of molecules, so it appears to move slower, but it has to go around all the molecules in the air, so the travel time is longer because it has to go farther. And when you get into a printed circuit board, the molecular density is even higher, so it takes it even longer to go through it. So it seems to move slower, but it's always moving at the speed of light. And the distance it travels is determined by the structure of the medium that it's moving through. But the other side, just remember, it can't go through metal. The crystal lattice of a conductor is such that the electromagnetic field doesn't go through it. It just interacts with the outside layer. The top, very few molecules in the outer surface of the conductor. So a little more as we get into the field behavior. And this is stuff Ralph tried to teach me for years, and I just couldn't believe it. It was too simple. And this is one of his best slides. If I've got a sphere, a conductive sphere, and inside there's a center conductor, and there's charge stored in that space, the charge will be between the outer surface of the inner sphere and the inner surface of the outer sphere. Remember, the charge is a function of some of these electrons moving to a different place. So that's the charge. It's a measure of how much displacement has occurred in electrons between these two materials. If there's not a hole in this outer sphere, there's no charge out here because of the charge that's inside here. It can't penetrate the metal. Same thing in a coax. If I've got a center conductor and with a shield around it, the field is going to be contained in that space, not out here, because there aren't any holes in a perfect coax. Unfortunately, we use cheap coaxes where there are holes. If there's holes, field gets out. Field is not very happy when it can escape. To take it now, when I've got the same sphere with a center conductor, and there's charge in here, and there's an opening, and there's another conductor, it will cause displacement of electrons between these two surfaces and achieve a charge in that space. If there's not a hole, nothing happens. But if there's a hole and there's another conductor, so the rule here to remember is between each and every pair of conductors in the universe, there will be shared charge. So between this conductor and this conductor, there's shared field. Between this conductor and a wire in the wall in your house, there will be shared field. Between that conductor and satellites in orbit, there will be shared field. Between that conductor and Betelgeuse, there will be shared field, because that's the law. Between every pair of conductors, there will be shared field. The only reason things work at all is because the magnitude of the charge is reduced by the square of the distance. So think about a printed circuit board. Thousands of conductors, all of them are sharing some of every other signal, every field on the board. And the only way things work is because there's enough separation between them that you can get signals from place to place. But we don't have any way to contain the fields. They don't give us coaxial interconnects on the PC boards yet. I keep asking, but they just laugh at me. But this is the idea. And then we take it a little bit farther. If you've got a plane and there are traces over the plane, most of the field is going to be in the space between the bottom of the trace and the top of the plane, because that's where the displacement is happening, and the most displacement. And here's another thing to remember. Surface area is everything. So this wide surface is where you have a large amount of displacement. So this is where the field wants to be. And that's one of the concepts of impedance. Now, there will be some field between the edges of the foil and these two traces, because that's the law. But because of the surface area is very small here versus the surface area on the bottom of the trace, most of the energy will be in this place. Now, just another idea, these circles are an attempt to show the magnetic fields, because a changing electric field will cause in the conductors that are bounding it a changing magnetic field. So that will cause this to be field. A constant or steady state, there will be an electromagnetic field, a voltage established in this space, and that established electric field will generate a moving H field or magnetic field that will be carrying the energy. Now, the reason planes are nice is because I'm not causing any, because the magnetic field has to be the entire surface. It takes an awful lot of electric voltage in order to create a magnetic field in this large conductor, as opposed to what's happening in the trace. So just a quick point out about crosstalk is a moving H or E field, when the switch is turning on, will cause a changing H field, the magnetic field. A changing magnetic field will cause a changing E field in the space next to it. And if there's any conductors in that changing E field will now cause a changing H field in that conductor, which will cause a changing E field in the next space. So that's how crosstalk works. That's how motors work. That's how generators work. You know, a generator is where we move a space that's bounded by a couple of conductors through the magnetic field, and it takes gulps. As it moves through, it creates an E field. It takes bites of the H field and makes it into E field. And in opposite for a motor, we cause a changing magnetic field, which pushes around the conductors in a motor and makes it turn. So all this stuff is really simple. They made it hard. It's not magic. It behaves the same all the time, and it's predictable. The other thing here is, if I have a trace underneath this plane, I was always taught you can't have sensitive analog in the same area as the digital clocks or fast signals, because it'll mess with it. Well, if I don't have a hole, there's no way for the field to go through there. I have to provide a path that's defined by two conductors and a space for field to move. So I can put a trace down here that's got a sensitive analog, and unless I give it a way to mess with it, it's not going to happen. So I can put a trace here and it's going to be happy. Now, unfortunately, that's not completely true because of the law of the conductors. between each and every conductor. So this field will actually go around the edge of the board and it'll find its way over here to this trace. The good news is it's about 200 dB from the top to the bottom of a plane. But again, because we don't have contained spaces, the fields are always spreading out everywhere. We're going to talk about electromagnetic waves now. When I was taking these classes, and I went to PCB West a number of years, and I'd go in there, and in each of the instructors would say something would be, some of it was the same, and some of it was different, and it was confusing. And you know, they would pay for me to go to these classes, and then I'd come back, and they go, "When are you going to teach this?" I'm like, I don't understand it well enough to teach it. I just can't do this. And so I kept putting them off. And then I got an email from a colleague that we were going to have a trade show or a customer event in Brazil, and that I was supposed to teach a PC board design class. And my response, because I like to travel anyway, was that I don't have a PC board design class, but I'm going to Brazil. So I put my foot in my mouth and said, okay. And I sat at my desk and I went, what am I going to do? I'm trying to think of what was start with something that all of these instructors talked about. And I came upon the idea of antennas. They all talked about antennas. So I'm like, first thing I want to do is I want to understand what an antenna is and how it what's its important. So I made this chart, and this is where the light bulb started to finally turn on. I started at 1 hertz, which is basically 6 times around the Earth. So, you know, 1 hertz is not something that antennas are something you can grasp. And I went to 100 gigahertz, and I looked at the changes. So at 10 hertz, we're looking at, you know, from Detroit to Honolulu. At 100 hertz, we're looking from Detroit to New York. At a kilohertz, we're looking for between 2 local cities, about 50 miles. At 10 kilohertz, we're still looking at, you know, 4.5 miles. So antennas are huge at these lower frequencies. At 100 kilohertz, we're looking at, you know, half a mile. So it's starting to get smaller. This is what the point here is that as the switching speeds increase, the antennas get smaller. At 1 megahertz, you're looking at 300 feet. At 10 megahertz, which is 100 nanosecond switching time, you're looking at 25 feet. So it's starting to get smaller. At 100 megahertz, it's 2.5 feet. And at a gigahertz, you're looking at 3 inches. So if something's switching in a nanosecond, which is a gigahertz, it only takes a 3-inch trace to be a radiating antenna. This was where, like I said, the light bulb started to turn on. So look at the idea of a quarter wavelength. When you look at this switching on and off signal in the analog world, it's plus 90, you know, 0, minus 90, back to 0. So a quarter wavelength is at the time it takes for the signal to go from 0 to 90 degrees. And at that point, the voltage is at maximum and it's stopped changing. So it's not being converted into a changing H field at this point in time. So if you're looking at a structure that's a quarter wavelength long, and you present it to you take a signal from a 50 ohm cable, and you put it into a dipole antenna, which is a 90 degree. So the corners where the energy is applied, and so what the field sees is a gradually increasing impedance until it gets to the end of the quarter wavelength antenna. At that point, its voltage is maximum. So the field it's presented to this space is the highest it can. At this point, you're at some impedance that's very, very close to the impedance of free space, which is 377 ohms. So the field doesn't know it's supposed to stop. It sees a more opportunity for displacement. So it moves into this new space from 376.99999 at the end of the antenna into the space. And that's how you can deliver the highest amount of energy into the space, and it leaves the boundaries of your circuit board or transmission system. So that's why a quarter wavelength is important. I'm like, what? that makes sense, you know. When I look at my table and I go to the part that really has something to do with our industry, that's when it really started to make sense. When I moved from Detroit, from Phoenix, where I was working, into Detroit to the automotive world, we were making a change from HMOS to HCMOS. And nobody seemed to have too much problem with HMOS. But you look at the antenna required, it's 26 feet. Unless you're working on a tractor trailer truck, a train, a bus, or a boat, a ship, you don't have anything big enough to be a radiating antenna. When we moved everybody from HMOS to HCMOS, and it was the thing, use these new parts, they're cheaper, they're faster, they're better, and every module failed EMC. And that's when I moved into automotive, was during this disaster. And when I saw this chart, it was like a no-brainer. Now, the antenna was less than 3 feet. What's connected to every automotive module? A wiring harness that's at least 3 feet long. So we gave them a radio transmitter. They hooked it up to an antenna, and we couldn't figure out why there were problems with radiated emissions. This is where the science was disconnected from the industry. And this was a problem in every market, automotive, consumer. Everyone was having problems because they didn't understand this extremely simple idea. When you get to nanosecond switching, it's 3 inches. So your circuit board's covered with hundreds, if not thousands, of structures that are capable of being radiating antennas. At the 65, 55 nanometers that are common now in the low-cost processors, it's the diameter of a pencil. The lead frame and wire bonds on a quad flat pack are long enough to be radiating antennas. So if you're not afraid, you need to be. This is getting to be hard. If you don't apply the laws of physics and design three-dimensional structures that define the space the fields move into, the results are what we know. We fail EMC. You have signal integrity problems. When you get down to these very fast signals, the antennas, a via is long enough to be a half-wave antenna. Structures on the die are large enough to be radiating antennas. If the field spaces are not managed carefully, there will be massive amounts of radiated emissions because we have a switch changing voltage and applying it to a space with a conductor that's a quarter wavelength. That's why things fail. So the idea is that when we created our design guidelines, the antennas had to be huge. They were always so much larger than the systems we use the devices in. As the switches got smaller and smaller and they were switching faster and faster, it's ratiometric. So if something's 1,000 times faster, the antenna is 1,000 times shorter. And we moved into this whole world without paying any attention to the impact on these switching events and the printed circuit boards. So suddenly we went from where the switch was so large that nothing was big enough to care to where the switches are so fast that everything is important. And this is what our world is today. So since TTL days, it was a 4-order magnitude change in the switching speeds of the devices we use. We did almost nothing to change our design methodology or in the instruction, what we're taught in school. What does that impact? It's huge. It's determined our destiny, which is to fail EMC. Ralph was big on orders of magnitude. And so a 0 order, this buggy can go 6 miles an hour. The first order change is now 60 miles an hour. This is a fundamentally different solution. The only way the buggy's going 60 miles an hour is if you put it on the back of a truck or throw it off a cliff. Second order is now 600 miles an hour, a fundamentally different solution. We're in a jet airplane. Third order, we're 6,000 miles an hour, and we're in a rocket ship. Fourth order, it's 60,000 miles an hour, and you're in an alien spaceship. Only in electronics will we try to make the buggy go fast. And we're paying for it. And again, this is where Professor Obeng and I are trying to help fix these things. So transmission lines. A lot of people hear the idea of transmission line and instantly go to control impedance. No, that's not true. A transmission line is any pair of conductors where there's field moving. It's the plumbing for the energy. So transmission line is two conductors, and hopefully you design it correctly, because in our world now, the transmission line, one conductor is ground, there's continuous dielectric next to it, and the switch conductor is the second piece of that puzzle. So why does the energy follow the conductors? The same reason that water flows in the stream. The banks of the stream determine the boundary of where the field is, or where the water is, and then the gravity, so the relative height over the surface of the earth, determines the lowest path for the water, goes to the point where the lowest point on the path. In the case of electromagnetic field, free space is 377 ohms. So you've got two conductors separated by infinity. As the two conductors get closer together, the space is reduced. So that impedance is lower. It takes less energy to fill that space, and the displacement occurs better. So as you get to smaller and smaller spaces, the field wants to go there because it takes less energy to achieve equilibrium, or that voltage, which is the field density per cubic centimeter. So if we get to anything lower than 377, it wants to go there. Every pair of conductors is a transmission line. What we want to do on the circuit board is to make sure that we have what I want to call a well-defined transmission line, that the energy is stored in the space between the ground and the switched conductor. Transmission lines are what we use. It's a lower impedance than space, so it's a place where the energy wants to be. If the switch is open, this transmission line can store energy. Where they are in the circuit is critical, because you need to make sure that the transmission lines are doing the job you want. At the wavefront, that's where you generate the changing electric field, which creates the changing magnetic field, which converts into a changing electric field, and that's where you get crosstalk. The energy is delivered to whatever's at the load, whether that be a switch, a motor, whatever. Energy moves both directions in the transmission line, and you can have more than one wave in a transmission line at the same time. And because you have changing electric fields, you create that changing magnetic field, which is causing the radiation to occur. So our job is signal traces one dielectric from the return or ground. That needs to be an adjacent trace if you don't have the luxury of ground plane, or one dielectric away from the ground plane. And anytime you break this rule, it's going to increase crosstalk and reduce signal integrity, decrease the immunity, and increase the radiated emissions. And unless a transmission line has to be controlled impedance, and that's where it's not lumped, which we'll get into that a little bit later. A 1/6 wavelength, if you're closer than that, then you don't need to control the impedance. So then you just try to use the lowest practical impedance, and that's based on the dielectric thickness and the width of the traces. So again, anything that's less than 1/6 of an inch, 1/6 of a wavelength, will be invisible to the signal. And we'll talk about why that's important. And that's why we could get away with everything in the past. We were always close enough to get to the components were close enough together that they didn't interfere with each other. So it seemed to work. But really what has to happen now is you need to know the transistor geometry. How fast are these switches turning on and off? And that determines what that transmission line you're connecting to, it needs to be. whether it needs to be controlled impedance or whether it just needs to be a well-defined transmission line where one conductor is ground, the other conductor is the switched conductor. The other thing most people miss is the z-axis. You can't take a via and drop it from 1 to 4 on a 4-layer board and expect the field to know how to get to layer 4. You know, it needs to have 2 conductors to show it the way. So if there's not a ground transition via for that signal, then it will find a ground somewhere and it will spread out going through the z-axis. And I've had a number of cases where customers' boards have failed EMC because they were missing one ground transition via. And that particular signal caused all kinds of trouble. When we go to the digital side, because we're mostly in a world where things turn on and off, you know, there's the analog perspective. So a square wave is made up of, you know, millions and millions of harmonics and pieces of wave. So you take this and you apply it to the idea here. Sorry that this is a little bit disjointed. What we care about in the digital world is from off to on, and that's a half a wavelength. And that's what's important when you look at what's being driven into a transmission line. There is no negative. It's from 0 to full voltage. So this rise time is important. And the distance the field travels during the rise time is the rise time distance. And this gives you an idea of what the behavior of the wavefront is going to be. So the idea is that when you have 2 parts that are far enough apart that you achieve something more than half the incident voltage before it gets to the receiver, is that there's going to be reflections that will cause problems. And we'll talk about that in a minute. So I use the 6th wavelength because this is a quarter wavelength. A 6th is down about here. That just means that the reflections are limited in their magnitude, and my layout team has more flexibility in placement of components. So this is the table from before, revamped for what we call lump distance. Like I said, I use a very conservative 6th wavelength instead of the maximum quarter wavelength. And when you look at this, in HMOS days, if the parts were in the same room, they were close enough. Even at the HCMOS days, if they're on the same board, they're close enough. That's why when I did my 68020 board, I wire wrapped it, and I thought it was because I was good. It was because all the parts were close enough together that they weren't having any problems. At a nanosecond, you need to have parts within about 2 inches, or you have to create a controlled impedance where the impedance matching is inside the 2 inches. At 100 picoseconds, you're switching such that the termination has to be in the die. That's where DDR4, DDR3, SerDes, all these very fast signals are terminated on the die, because by the time you get from the die to the circuit board through the lead frame wire bonds, you're way past lump distance and you're having all kinds of problems with what we call ringing. And this is the idea that when you go from a low impedance, if the impedance is the same, there's no reflection. You know, all the energy in that pipe goes through the hole. If you go from a low impedance, a driver, to a high impedance, a receiver, what happens is you've got all this field moving down the transmission line. It doesn't know what's at the other end. It gets to the end, and only some of that field is allowed to go into the receiver. And you end up with this field piling up at the end, and as it starts to reflect. And once the reflection is high enough that it's greater in density than the incident voltage, then now you've got a high voltage, it sees a low voltage, and it goes all the way back to the driver. And then it drops in voltage and causes a dip in the power. And then this now starts to source back to the receiver. And this goes back and forth until the energy is finally dissipated. It's either converted into heat, it's finally accepted by the receiver, or it radiates. Because again, every wavefront, you're translating some of that energy from E field to H field to E field to H field, and you're pushing these distortions or crosstalk across the circuit board. So this is why it's so important to know how fast these transistors are switching. So if I've got a switch, power source, and a load, and I'm farther apart than the quarter wavelength, I will start a flow of field energy. The wavefront is moving around. It comes to the receiver. Not all the energy can go into the receiver, so this bubble goes back the other way. So I see that this is now going from 5 volts to 10 volts. So I've got this bubble of field going back to the driver that's a higher voltage than what was sent. When it gets to the other end, it sees a low impedance, so that drops the voltage again. This causes drop now starts to go this way, and it goes back and forth and back and forth. This is ringing and crosstalk. It's not magic. It's where the receiver and the driver are farther apart than a quarter wavelength. So this is just a little description. I use the 6 because the maximum reflection I get is 67% of the incident wave. And then my design teams have some flexibility in placement. I hate control impedance. I do everything I can to avoid it. So if I can place parts so I don't have to put some type of termination device to match the impedance, then I will do so. If you can't, then every line at the driver needs to be terminated within that lump distance. It adds components and adds complexity to your design. If you're trying to route address and data lines on inner layers and you have to control the impedance on those transmission lines, in order to do that, you have to use a signal via to go from inside the board to the resistor on the outside with a ground via next to it. And then you got to have the resistor, and then you've got to drive it back down into the internal layers with a signal via and another ground via. So it really increases the complexity of your design. So that's one of the things you need to be aware of, and that's based on the transistor geometry of the driver. So power supply is the next thing you got to worry about. Where does the energy source need to be? You know, it's basically defined by the distance between the switch and where this energy is at. So it starts with on the die, then there's some energy stored in the package itself, the closest decoupling capacitors, and then finally you get to the power supply. It takes time for these waves to go there and come back. So it's all moved by waves. Again, this is the hierarchy. The farther away from the switch, the longer it takes to get there. So you can't get a nanosecond request for energy from a power supply that's 3 inches away. This is where you have to be understanding the nature of this transistors you're feeding, especially in the case of core transistors. Those are the smallest geometry on the device. You've got to know how fast they're switching so you know where you have to place that first capacitor, which is the only thing you can do. This is the first thing you have in your control. The rest is all defined by the package of the IC. And you have to go back and forth. So when you turn on a switch, energy starts to flow forward into the transmission line. Because the impedances are not matched, you'll see a drop in the voltage adjacent to the switch. And while you're moving energy into the transmission line, if it's a nanosecond, you've got a sourcing wave that's switching in a nanosecond, a gigahertz. The same time, you have a depletion wave moving back upstream at a gigahertz. It's a gigahertz event. And it goes back up trying to find energy. So it moves in that transmission line until it comes to a discontinuity, a change in impedance. That's where reflections occur. When the geometry changes, then there will be a reflection depending on whether it's higher or lower impedance. It tells you whether you source energy or you lose energy. And that's why it's so important to know this. So this is the chart that I made for power supplies. The consensus among the single integrity engineers that I work with now is that a rule of thumb is basically a 20th wavelength. Remember that digital circuit. The The good thing about this is if you want to look at a 20th wavelength, you're well inside the lump distance, so the ringing will never cause any kind of problem because it won't ring. At a 20th wavelength, you get time to make lots of reflections to bring energy because the transmission line has got a limited amount of capacity for this field, just like hoses. If you need 5 gallons a minute and your hose is good for 1 gallon a minute, you're not going to get 5 gallons a minute from a 1 gallon a minute hose because of the diameter of the hose. You either got to get 5 1 gallon a minute hoses, or you need a bigger hose that does 5 gallons a minute. It's all very simple to understand. So back to the discussion, when we went from HMOS to HEMOS, if the capacitor was in the same room, it was probably close enough. When you get to HCMOS, it's 6 inches. If it's on the same board, it's probably close enough. At a nanosecond, which is a very common switching speed now, it's about a half an inch. The good news is you can still physically place a capacitor within a half an inch of an IC. When you get to these very fast geometries, you're dependent on the semiconductor company to put enough capacitance on the die to take care of these fastest events related to the switching. And at these even faster geometries, it's not just on the die, but in the right place on the die, because the travel time, again, is a really important. If you've got a 28 nanometer transistor, it's switching in single-digit picoseconds. So it needs energy pretty quickly, and it better be on the die. You're going to find that there are parts that you buy that you can't make pass EMC if the IC vendor doesn't do this. So one of the trick questions I tell people to ask is, how much on-die capacitance is there for this device? Because if they don't know the answer, they probably didn't do it on purpose. If they didn't do it on purpose, there's most likely not enough. And there's nothing you can do to fix that. You're too far away on the circuit board. You're way past the 20th wavelength. So this is the idea, is that you really have to know the switching speeds and the geometry of the device you're using. This is absolutely critical, and we have to spend a lot of time identifying these facts in order to set the rules for a particular PC board. We're going to do a little bit of a wrap up here. Here's the fundamental key here. It's just electromagnetic fields travel in the space between the conductors, not in the conductors. There is current flowing, but it isn't the end all, and it's very slow. Electrons moving through these conductors are inches per second. It's really not very fast, or feet per second. It's nothing like what the electromagnetic field, which is moving at the speed of light. The switching speed of the transistors determines the frequency of operation, the nature of the transmission lines you require, and the power supply design. If you have a signal that switches once a year in a nanosecond, it's still a gigahertz signal. You have to design transmission lines for a gigahertz. You have to design the power supply for a gigahertz. The caps need to be within a half an inch, and you have to terminate that transmission line if it's more than 3 inches away. Every switched conductor in that signal and power need to be one dielectric from ground, from the source to the load, in all 3 dimensions, X, Y, and Z. Ideally, it's an adjacent plane. If you don't have the luxury of having planes throughout your board, then you use a coplanar trace that's ground, so that you put some definition to allow for the continuous dielectric to be bounded on one side by the continuous conductor and the other side by the switched conductor. A 4-layer design, which is very common in our industry. If layer 2 is ground, 1 and 3 are automatically good transmission lines because they are one dielectric from ground. If you route from layer 1 to layer 3, you have a good transition from the dielectric between layers 1 and 2 to the dielectric between layers 2 and 3, because there's a hole around the via for the energy to move through. So you have continuous conductor, the ground plane, you have a continuous dielectric because of the hole around the via, and the switch conductor goes through, is that one. So you have this continuous space. When you go to layer 4 on a 3-layer board, you have to route it as if it was a single layer board. Layer 4 is not related to layer 2. I don't care what everybody thinks. In our industry now, it's too far away. There's 2 dielectrics in a signal layer between 4 and 2. Layer 4, you have to route it with coplanar ground traces. And I do that with a combination of flood and traces. When I go from 1 over 3 to 4, I must have a ground transition via to connect those horizontal dielectrics between 1 and 2 or 2 and 3 to the vertical dielectric, so a ground transition via to connect it to the horizontal dielectric that's on 4 between the adjacent conductors, the signal trace and the ground trace or ground flood. And here's something a lot, I have a noisy ground. Ground can't be noisy. It's one conductor. Noise is unwanted changes in field density. If there's noise, it's because more than one signal is allowed to share the same space. If you want to have no noise, you make sure that every signal has its own place to live. If you don't, then you're going to have problems with multiple signals in the same space, and they will affect each other. And then people are always talking about special grounds and analog grounds, and we'll talk more detail about this in the class tomorrow. But Dr. Hubing repeatedly says, thou shalt not split ground. It is almost impossible to create discrete domains to move energy with multiple grounds. Is it the best solution? Certainly. If you can create completely discrete domains for every signal, that's wonderful. But you can't afford to do that. Not in the cost of materials, not in the physical space it takes to do that. The way we work things is to use a common continuous conductor and make sure that we present each signal into a space that's bounded on one side by the switch conductor and the other side by the continuous conductor, which connects that dielectric where the energy is moving between the source of the energy to the destination or the load. Anytime you break these rules, the one dielectric rule, you're going to cause some impact on the signal integrity and the EMC behavior of the board. Is it always going to be enough for failure? No. But Murphy says the one time you break the rules, it's the one that's going to cause you to fail. For instance, my customers with the single missing ground transition via. If it's the wrong signal, you're going to have a problem. The rule of triplets, you have to pound this into your brains. You get 3 components: conductors, spaces, and switches. And you can only do 3 things with field. You can store it, you can move it, or you can convert it to kinetic energy. Make something wiggle. It's not rocket science. Here's the perspective you need to adopt. We are just plumbers with very, very leaky water pipes. We're creating 3-dimensional spaces to manage the field to move in. It moves right to left, up to down, across, the idea of not managing the z-axis. It's like putting a water faucet in your basement and not putting any pipes to the upstairs and turning the water on and expecting the water to make it to the upstairs. Well, eventually it will, but you won't like the results. The same thing happens with fields. If you don't give it that z-axis plumbing with the signal and the ground via next to each other, the energy will find its way there, but it will spread out through everything. And it will cause problems with the other signals as well as the one. So I've been very fortunate to meet and become friends with Rick Hartley. If you get a chance to take any of his training, please do so. Rick has actually changed his philosophy a bit over time because I was able to introduce Rick and Ralph together and they started collaborating as well. My mentor, Ralph Morrison, who unfortunately we lost in 2019, his patience and his dedication to teaching me has changed my world. I designed my first network control board a couple of years ago, a gigahertz 28 nanometer network processor running with 400 megahertz DDR4. I had an Ethernet control processor. There were Ethernet switches. This board had SerDes and PCIe and Ethernet and CAN and LIN and everything you could imagine in Aurora interfaces. 60 picoseconds was everywhere. Two PMIC and two switching power supplies. I took 26 inductors and ferrites off of the reference board the company had. It caused a lot of distress with the applications team. My response was, this is my board. If it doesn't work, I'll do it again. Followed the rules that Ralph taught me. It passed EMC the first time. Well, this is state-of-the-art stuff. The core needed 7 amps per microsecond. I followed the rules. I was a little apprehensive, but I kept telling myself, trust in Ralph, and it passed EMC the first time. All of my designs always pass EMC the first time. I'm not that smart. The rules are that simple. If you follow these rules that are based on the simple facts that we've discussed this morning, you're going to be successful. Also, I was lucky enough to become acquainted with and friends with Dr. Todd Hubing, and he's now, Rick and Todd both are independent consultants, and they teach classes and do a lot of great work in helping people to identify the issues with their circuit boards and systems and be able to change the design to match compliance, because Dr. Hubing has since retired from Clemson. I have a list of books that Rick Hartley has determined to be useful. The first one here is Ralph's book, Fast Circuit Boards, and then some of the books by Lee Ritchie, who's a supercomputer designer, and Hall and McCall. And here's one, you always got to have Dr. Johnson on here. He's also did high-end computer systems. And then the Eternal and Eric Bogatin, which hopefully you'll get a chance to take some classes from him as well. Eric does a bunch of seminars online as well as I do, and has written a number of books. Some more books. Dr. Bruce Archambault, who was a server, he worked on the Blade server team at IBM. Another brilliant guy. The only caveat has, a lot of these guys are teaching things from their perspective, and their experience was in geometries that were not the same as what we're facing today. They didn't have 2 nanometer devices coming at them. They were still in TTL days. So some of the things they teach are not completely going to be the right perspective for these very fast circuits, but there's some good foundational advice in those as well. The books, this is some things I put together. Again, Ralph's got his last 2 books. One of the things he's told me when I first contacted him, it was basically, who are you and why are you calling me? Because Ralph was very much retired at the time. He was in his 80s. And we were going to have a conference, and I was lucky enough, or unlucky enough, depends on your perspective. My boss was on the content committee for our first Freescale Technology Forum, and he had to be somewhere else, and he asked me to sit in on the meeting, and I was freshly from PCB West, so I was really geeked about the idea of signal integrity training. And we were moving to 90 nanometers and smaller for our processors. and our customers couldn't, get TTL to move past EMC. So in a lull of the conversation, I went, we have to have signal integrity. It's our responsibility. Customers are failing EMC. And to shut me up, they said, okay, you can put together a panel of experts. And I'm like, okay. So when I got back to my desk, I went to my shelf of books, because being any good pretend signal integrity guy, I had bought every book that I could, including one from Ralph and the ones from Dr. Johnson. So I started calling all the authors, and none of the big guns could come because there was a conference in the UK the same week as our conference. So all these guys were committed. And I finally got to Ralph and found a phone number, and I left a voicemail, and he called me back and he said, "Who are you and why the hell are you calling me?" I said, "Well, I'm Dan Beeker from Freescale, and we were having this panel of experts, and I'd really like you to be on it." So we got to a discussion, and Ralph agreed to come. And that's where I found out he was a physicist. It was great. So now I have my science guy. I was able to get a couple of the instructors from PCB West, including Mr. Hartley. I was able to get two of the researchers from University of Missouri-Rolla at the time, because Freescale at the time was a consortium member. So I had a little bit of clout. So I got Dr. Juniak and Dr. Hubing to come and teach. I had a friend who was the chief technology officer for X2Y capacitors. And then I also was able to get hold of a graduate from UMR who was a respected EMC consultant, Lee Hill. So this was my progression from science to applications in a component. So the X2I guy went last. So Ralph went first, and by the time they were done, Ralph could hardly contain himself. We finished the panel. This little old man is jumping up and down, going, "They've got it wrong. They've got it wrong. That's not how it works." And I being the host, I went over and said, "Okay, Ralph, calm down. Let's go have lunch, and you tell me about this." And he started to tell me about halls and walls and spaces, and I'm like confused, but I know he's got to be making sense because he's the physicist. And so I started hiring him to come and teach classes for my customers. And the result was a collaboration where he went to write new books because he hadn't written anything for a few years, and then adopt me as his apprentice, and he was going to teach me field physics or kill me trying. Luckily, I was able to finally get it. So before his passing, we created a website, ralphmorrison.com, in order to help spread his knowledge. And Ralph never let anybody video him until he had just written the last book. I went to Ralph and I said, "We really need to be able to capture your legacy, your knowledge, and I will hire a videographer. We will create some professional videos. You can review them and approve or disapprove them." So he let me do that. And on the ralphmorrison.com website, there are 3 2-hour sessions of Ralph teaching his last book. It is a pay-per-view. You pay $25 or $50 depending on how many downloads you want to do, and all the proceeds go to Ralph's widow. There are also links to where the list of his books. Most are still available from Wiley or from Amazon. So this is a good resource to go to. And I'm trying to keep it updated with links to real things, but I'm not a very good webmaster yet. I'm still struggling with WordPress. PCB West, if you can go to a conference, go to PCB West. I've been there every year for the last 15 years, and now for the last 6 years, I've been one of the instructors. So I teach there. A friend of mine, Doug Smith, has EMC ESD. He is the best at troubleshooting. He can help you figure out what the source of interference is, where it's affecting your circuit board, and then help make suggestions on how to fix that. He's got hundreds of application notes on his website. A lot of it focused on helping you to build your own test and measurement equipment at the lowest cost. So how to make current probes and all kinds of fun things in the low end. My friend Ken Wyatt is another EMC consultant. He's written a number of books, and he's got lots of seminars on his. Another friend of mine is Derek Walton. He has a NARDI certified test lab. And so if you need any support from testing, he's there. Again, the IEEE EMC Society has a lot of work they've done to try to help people understand the physics. Just a note, Dr. Hubing was past president of the IEEE EMC Society. He also has written a large number of application notes and papers. Clemson still has a website, and I think they're still following Dr. Hubing's path. There's a couple of websites, one's automotive specific and one's EMC. Grand Valley State has things on their website, and then the Missouri University has stuff on their website. And then, of course, about materials and standards, the IPC has a website with extensive documentation that's used for designing boards. And I'll leave you with this final statement that Ralph kept saying and I kept missing. Like he said, I was the first person who ever finally listened to him. And I find that to be a great tragedy. We've lost a lot of knowledge. And I want you all to try to focus on this statement. Buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. So I want to thank everyone for your kind attention. I really hope that this has been something you'll find useful in your day-to-day work. And you're certainly all invited to join us tomorrow, where I'll talk about some things you need to do while you're designing your printed circuit boards and to help improve things across the board. So Eric, if you would like to make any closing remarks, then I'll stop the recording in just a minute.
All right. Thank you very much. I wish this was going to be a week-long program. I don't know if anyone is having any question to ask. Maybe you can spend some few minutes taking some questions. Okay. All right. So is there a hand up? No hand up. All right. So I think we are about 18 minutes late, but it's worth it. And I wish we would have a full house tomorrow. Today was impressive. And Mr. Daniel Beeker, I think I would like to thank you very much for your time. It's a very great training. I'll be uploading the video latest by tonight. That'll be around 12 a.m. GMT. So those who would like to take a second look at it, I will push the link to our PCBAfrica platforms, and I'll also email the links to all those who have registered. I think that will be all from my end. So thank you for coming once again. See you tomorrow.